Okay.
I will use the excuse that I was in Taiwan last week visiting collaborators. I arrived back on Sunday morning, and at the moment I think it's about midnight. So, yes, so the galaxies, the halos collide, and the galaxies they host collide with them. And it carries on, then the new galaxies collide with other new galaxies or old galaxies, and then eventually you end up in the modern day. And generally speaking, all galaxies in the universe either have merged with something or will merge with something. So it happens for everything. And it will happen to us too. This, hopefully you recognize, is a nice picture of the Andromeda Galaxy. It's our nearest big neighbor. And in about 4 billion years' time, the Milky Way and Andromeda are going to collide. And so, unlikely anyone in this room will be there when it happens. But if we're still about in 4 billion years' time, it'll be kind of useful to know what's going to happen. So if the science doesn't interest you, maybe the future will. So how do we find galaxy mergers? And for most of this seminar, this talk, I'm referring to galaxy mergers, meaning major mergers. So the two galaxies colliding are roughly the same mass, like ratios of up to about 1 to 4. Then you get minor mergers, where its ratio is about 1 to 10, and then you get mini mergers, which is tiny. So there are, generally speaking, 4 ways to find galaxy mergers. As I already said at the beginning, sort of half joking, we can look to see if we can see them. There's something called the closed pairs method. We can look at the morphologies of the galaxies, so the fact that they collide and mess each other up can help. And in the last 6 or 7 years, we're now using machine learning methods as well. So visual classification is fairly obvious. I can show you this galaxy, you can look at it, and you can tell me it's not merging. Easy. I can show you this galaxy, you can look at it, and you can tell me it's merging. Easy. I can show you this galaxy, you can look at it. Is it a merger? I mean, you've got a bright patch here, it's kind of curvy, faint over here, maybe it's 2 galaxies colliding. Not so easy. Or you have your coffee in the morning, and you're like, no, that can't be a merger. You can't see 2 galaxies, it's just some kind of irregular mess of something. Or you manage to sleep well, you're not tired like I am at the moment, and you've had your morning coffee, and you're like, no, actually, I was right the first time, it's a merger. Both of these answers, to a degree, are correct. We don't know the truth of what this is, we just kind of have to make our best guess. The problem is, I suspect everyone in this room and everyone online has made an opinion about what this is. I guarantee not everyone agrees. And I know I don't agree with myself when I do this. So visual classification's not reproducible by yourself, let alone in a group of people. So we need something slightly easier, slightly better at being reproduced. So we can turn to what we call the close pairs method. In this, you pick 2 galaxies that are close on the sky. We're saying roughly 50 kiloparsecs in separation. And they have to be moving slow enough to end up gravitationally bound to each other. So this is normally taken to be about a difference in speed of about 500 kilometers per second or less. To do this, you take a spectra of one of your galaxies, work out its redshift, take a spectra of the other one, work out its redshift. The difference in redshift, if it's less than 0.002, they're probably going slow enough to become gravitationally bound. Of course, this is not a cheap thing to do. You need to get time on the expensive spectrographs to do this. If you're using a multi-object spectrograph, and your galaxies are close together but at high redshift, you get fiber collisions, so you can't necessarily get the spectra of each galaxy. So despite this,
I can't read this infrared redshift.
Sorry?
This is an infrared, so I can't see the redshift.
Sorry, I mean, this is just, I don't think these are the real they're roughly the redshift of this galaxy. The exact value doesn't matter.
Same thing.
It's just, so this one is, I've said it's 0.0339, and this one is 0.0341, but it's just to illustrate the idea. So they're expensive spectroscopic observations, and they can be contaminated by flybys. So if you're wrong about this relative velocity, the two galaxies can interact with each other, then carry on and pass off into them. So they don't actually end up merging. And this can be a factor of up to half of these selections. So it's a good method, but it's expensive and it's not perfect. Galaxy morphology, this one's fairly obvious, I think. Mergers disturb galaxies, so they change the morphologies. So typically you have cuts in one of two parameters. You can use Gini and M20 cut, where Gini is an expression of how light is distributed between pixels. And M20 is got a really nasty name that I can never remember properly. It's the second moment of the 20th percentile of the light, something like this. But what it effectively is a way to say how far apart the bright things are compared to the other bright things in the image. You can also use asymmetry and smoothness. Asymmetry, of course, is how asymmetric it is rotationally. So you rotate it by 180 degrees, subtract from the original image. What you have left is your asymmetry. And smoothness is just a description of how clumpy your galaxy is. These are relatively speaking simple to calculate. There are half a dozen, if not more, different software that will calculate these parameters for you relatively quickly. But to get the best parameters, you need high quality observations. If you have high quality observations, again, it's a cost that you need to deal with. And generally speaking, these parameters, you do it with one data set, you get one value, you do it with another one, you get a different value. So they're not consistent with the same object. If you change surveys, change data. And as examples, they don't really quite work very well. This is a plot of Gini versus M20. M20 is going backwards, but just because it looks slightly nicer. And these two lines, they're cut in the Gini M20 parameter space that should separate galaxy mergers from non-mergers. So if you're below this line, you should be a galaxy merger. If you're above this line, you should be a non-merger. The color scaling is based on visual classifications. So the Galaxy Zoo project classified thousands of galaxies, in this case from the Kilo Degree survey, kids. And inside each of these bins, I take the average of what's called merger neither frac. Sorry, I had this backwards. I told you I'm half asleep. The bottom one should be non-mergers. The top one should be mergers. So mergers above the line, non-mergers below the line. Anyway, so inside each cell is the average score given by the people who did the Galaxy Zoo. Below our line, we're nice and blue, which means most people thought all these galaxies are non-mergers. Great, it's working for us. Above this line, we should be seeing fuzz of red. This is mainly blue. There is a kind of valley of reddish colors very close to these decision lines, but obviously this cut is not working. When I was saying that different data sets don't work well with each other, these cuts were based on, I believe, SCSS and background of kids. Our morphological parameters are not consistent between surveys. So is there something we can get that's consistent between surveys? Probably not, is the spoiler. There's reproducible, unlike visual classifications, and is cheap, unlike the close pairs. So let's try machine learning, deep learning. The justification for this partially is the Euclid survey and the VRC Rubin that should be coming online next year. They're expecting order of 1 billion galaxies. And you want to classify all of them because you like lots of statistics. So let's say if you get a human who is very good at doing something, they can classify 30 galaxies in a minute. I have reached this rate before. It didn't last very long. But to do 1 billion galaxies, then you need, 500,000 hours. Non-stop, no sleeping, no eating, no anything, just classifying galaxies. That's 63 years, or the entire professional career of one person. So I think you can agree that's not really feasible. In machine
How many
learning,
cosmologists are there? Like, surely more than 63.
yeah, but then they're not cheap either. So if you do machine learning, these are now probably 4 years old, these statistics. So I could do, 500 a minute, which gives you about 35,000 GPU hours, or about four years. So still not quick, but if you want 63 people, you have to pay, everyone's salary for 63 people to do nothing but classify galaxies for a year. If you want to do it in a year, you need 4 GPUs, and they cost, 2,000 zloty each, compared to say 10,000 zloty per person per month. And then, okay, GPUs plus electricity, but I think GPUs and electricity are cheaper than using all the cosmologists, as you say. So it's quick, it does things better, and it's reproducible. You put the same data in, you get the same data out. It doesn't have a problem with being tired or needing coffee or having to have too much coffee. But
No union.
sorry?
No union.
No unions. You can make them work all night, they don't need to sleep. But the results are only as good as your training data. And again, if you switch to a different data set, it doesn't really quite work very well. So there's problems. Most of the rest of this talk is going to involve deep learning in some respect. I'm not going to explain how it works because that's an entire seminar on its own. So this is how the ways to find galaxy mergers. So how have we actually been finding galaxy mergers? Till now, it's all all on paper. Let's put it into practice. Let's start in the North Ecliptic Pole. This is a 5.4 square degree extragalactic field that's in the North Ecliptic. Has extensive wavelength coverage from X-ray to radio. So whoever in this room likes a specific part of the spectrum, you have data there. Importantly for me, for what we were doing, has deep hyper-supreme-cam HSC imaging. This is optical imaging. So you get nice pictures like this one. It's also a target for a Euclid deep field. I think the data for that should be coming out soon. I'm not in the Euclid consortium, so ask someone who is. And up until about 2 years ago, it had no merger catalog. So we didn't know if there are any mergers in this field at all. So I decided to make the merger catalog. I need some training data. I used data from the Kids Galaxy Zoo project that we just saw some results of before. These were selected with an asymmetry smoothness cut ratios below 0.15. I wanted, and they have the gamma fields have HSC data, so we can move to NEP without too many problems. This is what one of our galaxies look like. This is a nice merger, redshift 0.09. But we want to go higher redshift than 0.15. That's a bit close, especially in the era of James Webb when you get to like redshifts of 12. So we augment our images so we can get to redshift of 0.3. So you make them the right size, the right brightness, then you add noise, because if you make them less bright and smaller, the noise qualities change. So we make them look more or less like real observations, or as close as we can get. Then we feed it through machine learning methods. We use what's called a convolutional neural network, which is used with images. Feed your images in, there's a convolutional neural network, what I call a deep neural network, or feed-forward neural network if you prefer. This does some deciding. But this is just images, and we know morphologies are useful as well. So we also included morphological parameters. For example, concentration, asymmetry, and smoothness. We feed that into our network as well, and we get some results. So you just get some outputs. What's the probability it's a merger? What's the probability it's a non-merger? And I can give you some statistics. I apologize for death by tables. Redshift of less than 0.15. Our accuracy is about 88%, which is quite good. And we recover about 86% of our galaxy mergers. Higher redshift actually drops, as you might expect, because things are smaller and it's clear. But accuracy of 85% is quite good, and we're recovering 79% of our galaxy mergers. When you actually, these statistics, generally speaking, from anyone who writes a paper about this kind of thing, slightly misleading because their data sets will be balanced. In reality, we expect about 10% of the galaxies we observe to be galaxy mergers. So these balanced statistics don't quite work when you give it real galaxies. So 7,000 redshift less than 0.15. The network says 1,500 are galaxy mergers. We went and checked. We think about 250 are actually galaxy mergers. So it doesn't really solve the problem of it gets it right. It kind of doesn't get it right as good as we would like. Then a high redshift, something similar, just under 30,000 galaxies, of which just under 9,000 were found to be mergers, of which we thought about 1,900 were actually mergers. So this ends up less than roughly 10% of our galaxies that we put in are actually what we want them to find. So nice results, just not perfect. And I haven't shown you any images lately, so here's some images from our network. This is what the non-mergers look like, just kind of round blobby things. What we call the merger candidates, so what the network thinks are mergers. These make sense. There's two close galaxies, these two probably close galaxies here, so maybe mergers, but we checked, they're not actually mergers. And then the ones we visually checked. Here you see two galaxies in each of these three images close together, interacting with each other, actual galaxy mergers. So what is the network looking for? This is a very difficult question to answer. The short version is faint structures. So these are what we call, this is an occlusion experiment, where you hide some pixels, run it through the network, see what it says. When you've hidden a pixel, once you've done it all, you take the average of when that pixel is hidden, what the score is, and it gives you these kind of heat maps. And what you see is when the secondary galaxy is hidden, the network thinks it's more likely to be a merger, more likely to be a non-merger, although the difference is not very big. If 1 here is a merger, 0 is a non-merger, these are very close to 1 all the time. And also, if you hide the faint structures in both of these images, the network thinks it's more likely to be a non-merger. So faint structures are important, which we'll return to later on. But this is images, this is morphology. We also get photometry, just, simple things. So in the Sloan Digital Sky Survey, we think merging galaxies can look different photometrically. I said before, the star formation rate changes. If your star formation rate changes, you get an increase in UV emission, and you can also get an increase in the infrared emission. CNNs are slower than DNNs, and images require a lot of pre-processing. So the way you scale the images, how big the image should be, how do you cut it, this kind of. But photometry is relatively simple, right? It's just a number. In this case, the U-band of this image is 16.4. The magnitude is 16.4. It's easy. So a PhD student, Luis Suarez, who is defending his thesis next week on Monday, he took this idea and he started to play around with it. So he needed training data because he's doing machine learning. So SDSS has Galaxy Z results that gives him his classifications. He had about 3,000 galaxy mergers, redshifts less than 0.1. He picked 3,000 non-merging galaxies to train for merger and not merger. SDSS is an optical survey, so it has UGRIZ band photometry plus the associated colors. And there's 6 different magnitudes. One based on PSF, one fiber, which is an aperture magnitude, 3 different light profiles, and then model, which is a combination of these 2 exponential and Dirac-Cuviers light profiles. And what he found was kind of interesting. So here we have validation accuracy and different types of model magnitudes. So B here is for bands, C is for colors, BC is bands plus colors, BCE is bands plus colors plus errors, and then the 3 BCE are just different ways of normalizing the errors. If you do the bands, it's about 65% accuracy. Colors, about the same. Surprisingly, if you join bands and colors, it goes up to 69%. Colors are just a linear combination of bands, so why does this jump? Apparently it's useful. Then you add the errors, and your results increase very slightly. This is just for the model magnitude. So if we now look at all of the magnitudes, you see something similar. Bands and colors are the worst. You join them together, it increases. So this orange line and the shaded area correspond to the bands plus colors for the model magnitude, just so you can easily compare them. Then you include the errors. So let's say petroleum goes from 69%, 85%. The fiber magnitude goes from 65% to nearly 90%. This is weird. This is errors. Errors shouldn't be helpful. Just to tell us how wrong we are about something, not to tell us how right we are about something. So Luis then looked into what the error is. The error in this case from SCSS splits into 4 components. There's the fiber counts, error on the sky, there's the dark variance, which is to do with the instrument itself, and the error on the sky background. So you put all of them together, run it through a network, you get just over 90%. Remove the sky error background, just over 60%. Fiber count sky error is over 90, dark variance, which shouldn't really do anything, plus sky error, again over 90, just sky error on its own, 83, 84%. So why would the error of the sky help? We think this is because of background features. I was saying before the neural networks were looking for faint structures. When you work out the sky error, the sky background and the error on it, if there's faint features, your error will change. And you can see it in this plot. So this is 2 sky errors against each other. Sky error for the R band, sky error for the G band. The purple pluses, if you can see, are non-mergers. The orange crosses are mergers. You plot them in this parameter space. Up here you have main mergers. Down here you have main non-mergers. So it's like the error is bigger when you have a merger, we think, because you mess with the galaxy, faint structures flow around, you pick it up when you work out the sky error. And then Luis was like, hang on a minute. This is splitting. Let's draw a line here. Draw this line. Your accuracy of your classification is now 91, 92%. It's about the same as the neural network. You do all this new complicated work with neural networks, and then it turns out you didn't need to do it. You just look at the sky error and it splits for it. So I don't know who here works with neural networks, machine learning, but it's worth checking why your system is doing what it's doing, because it may end up that it's telling you something really interesting you'd never thought of, that ends up being easier and cheaper to do than complicated neural networks. So this is, of course, assuming we know what a galaxy merger is. This is a slightly weird thing to say, but we don't. The truth is unknown, right? I was showing you this picture of, here is a galaxy, what is it, merger, non-merger? And you probably now have your opinion on what it is, and the person sitting next to you has a different opinion. So and you're both right, and you're both wrong, because we just don't know what this is. So we're doing things that we don't really know what the truth is. But simulations know the truth. You can simulate something, you can follow a galaxy through the simulation, find out when it's collided with something, that's a galaxy. Except, sort of. Because when the time resolution might not be good enough to find the point where they actually merge. So you have to have some kind of scale of when the merger begins, when the merger ends. And to have this scale requires a person to say it should be this much time before or this much time after. So simulations are the closest to the truth we can get, is probably fair. But then we can use it to train things as well. So if we go back to how we can find galaxy mergers and think about what we've been talking about already today. So what can we use to find galaxy mergers? Well, machine learning seems to work reasonably well. We know fate structures are important, and we know simulations give us some semblance of what the truth is. So how about, and this is what a student in Jagiellonia has been doing with me, David Hoodie, if we can somehow use just the fate structures, does it do better than the images? Does it remove some ambiguity of our classification? So these are images from the illustrious TNG simulation that have been processed to look like HSC images. What David did was he modeled all these galaxies with a Circic profile, which gives you the center sort of model image. This is just the Circic profiles of all these galaxies. Then you subtract this model from the real image, and it gives you a residual. So this left image is everything. The middle image is a simple model of your galaxies. The right image should therefore be just fate structures. So we trained a network on each of these three data sets, and we have the raw image, the model image, and the residual of the same set of galaxies. And again, these are results from occlusion experiments. The raw image does what we were seeing before. Is interested in the fate structures around the galaxy. The model, you hide the central galaxy, and it thinks it's a non-merger. And there's no fate structures, so it's not really looking at fate structures. Then the residual image, which is just fate structures, doesn't really care about the middle where the galaxy should be. It's all the stuff around the outside, so it's looking at fate structures. I mean, this is probably, well, obviously, but unless you actually test it, you don't really know for sure. So what he got was on the original image, he got 74% accuracy, which for this data set, other people have used it as well. This is more or less what people tend to get. So this is normal. But just the models, he got 70%. But if we think the fate structures are important, the models don't have it. So obviously the distribution of light, the simple distribution from a Circic model is important as well. And then the residuals that we were thinking this should be the best, remove all the noise of kind of the boring Circic profile, just leave the interesting stuff. Actually does the worst, 68% accuracy. So you need the fate structures, but you also need the boring normal structure to be able to do classification. And he's now, there's still some work to do on this. We're hoping to submit the paper soon, but he's going to apply it to galaxies in NEB, compare it to the catalog I discussed before, and compare it to Galaxy Zoo results to see what each of these different things is giving. So that's, why we care about galaxies, how we can find what a galaxy is. What are the galaxy mergers we find in the last 10 minutes? Maybe, unless it needs to be quicker.
We have 12 minutes.
So again, we're using the truth of a simulation. Let's just see. I'm interested for this in galaxies from kids. So let's make TNG simulation images be perfect from the simulation, but have properties of kids' images. So the same pixel scale of about 0.2 arc seconds, and the same values, U, G, R, I. And this is the bit where I say, we have to put limits on something. I have selected if a galaxy will merge in the next 1000 mega years, or has merged in the last 500 mega years, it's a merger. And this is kind of what they look like. And what we're going to do now is try and find the time before or after the merger event. So we put it in a neural network, and this is kind of what we get. So this is the prediction from our network against the truth from the simulation. These are normalized. I tried to not normalize them, but I lost the code to make this plot. So 0 is 500 mega years after the merger event. 1 is 1000 mega years before the merger event. If we were perfect, everything should lie on this red line. We're not perfect because neural networks never are. If anyone says they have a perfect neural network, they are lying to either you or themselves. But we do this training and we end up with an average error of about 250 mega years and a mean error of about 190 mega years. So we're not perfect, but not too far off, considering this is quite a difficult problem. Like I said, I want to apply it to kids' galaxies. So let's make those perfect illustrious TNG images look more like kids. So convolve them with the PSF, add observational noise in the background, a few other things. And then we end up training on about 120,000 galaxies that look like kids' galaxies. And this is what we end up with. This time it's not normalized, despite what my captions say. So negative numbers are time after the merger event, positive numbers are time before the merger event. Everything again should be lying on this red line, and everything again is not. The results we get are worse than in the kind of idealized case. So average error is about 325 mega years. Median error is about 209 to 300 mega years. The difference is only the noise in the image and the PSF. So we've destroyed the faint structures that we know are important from this TNG images. And what's left, we've buried a lot of that inside the noise. So you lose a lot of information. The network has a harder time picking things up. So your results are worse. But what we do see for pre-mergers, it can reasonably well identify them from predictions. Post-mergers, it can reasonably identify them as well. It's not doing a very good job of getting the time. So I said we're doing it with kids' galaxies. We find 13,000 kids mergers that we've already identified, run them through our network, and we get some results. And the results, I think, look reasonably okay, right? So here is a collection of 9 randomly selected mergers that I've now ordered by time. The one that's about 58 mega years before the merger event is believable, right? You have the center of your galaxy, there's some structure around it. It should be starting to become one galaxy, so you lose the second nuclei. That looks okay. Second panel, depending how tired you are, like me, maybe there's 2 nuclei in the center, maybe there's 1 and it's a very disturbed galaxy. So it's not the best result, maybe, but it's believable at the 180 mega years before. This next one, C, you can see the 2 galaxies. So 188, maybe it's reasonable. D, you can see the disturbance of the galaxy. So at this point, it's probably 2 galaxies that are passing each other. So they've just kind of collided, stuff is thrown around everywhere. Panel E is the one I was concerned you wouldn't be able to see. I'm not sure if you can see it. 2 galaxies are here. I can see it, but I know what to look for. You can see the two individual galaxies, so a bigger time makes sense. Going to the ones that are easy to see, panel F, your galaxy is all kinds of disturbed, so it's probably a long time before. G, you can clearly see two galaxies, and these are, throwing things around, so they're possibly first approach, or just past first approach. And then the final panel is question. So I think most of the time it's giving you a reasonable estimate of the time, plus or minus the 300 megayear uncertainty. So we have all these times for these mergers. So we can do something with this. For the first time, we have times of galaxy mergers that are pre-mergers and post-mergers, the entire spectrum. Let's do some fun science in the last 5 minutes. So we take our 13,000 KISS galaxies, we match them to non-mergers. In mass, because star formation rate and mass have a dependence. In redshift, because star formation rate and redshift have a dependence. And in local density, because star formation rate and local density have a dependence. So we want the only difference to be, is our galaxy merging or is it not merging? So we match our galaxy mergers to 10 non-mergers. And we can work out the star formation rate enhancement, star formation rate change. So in this case, delta SFR is if we take the log of the star formation rate of our galaxy merger and subtract the average log star formation rate of our non-mergers, we get delta SFR. Positive values are an increase, negative values are a decrease. So 1 is about a factor of 10. 0 is there's no change, -1 is about a factor of 10 lower. So here we have delta SFR as a function of merger time for the first time for the entire sequence. And you have two populations. You get this enhanced population at the top and the suppressed population at the bottom. So we bin this by merger time into bins at about 250 megayears, which is comparable to the uncertainty that we have. You can see these two populations. So this is delta SFR, this is just the number of galaxies. There's these two populations, the suppressed and the enhanced. Fit a double Gaussian distribution. The lower Gaussian is the suppressed population in red and the enhanced population in green. We do this for all our bins and we get something else. These red squares are our suppressed population, more or less staying constant. There is a slight indication that it might rise just before the time of 0 and might drop just before then. So weak indication, maybe we think these galaxies are dry, so they don't have much gas in. They approach, some of the gas that's left is ejected to give you this slight decrease. It then falls back into the galaxy to give you this slight increase again. But it's just very slight changes, so it's a bit maybe. For the enhanced population, it's clear. As you get closer to 0, your star formation rate enhancement increases. This is what we see in simulations all the time. This is what you see if you look at separation of galaxies. Closer they are, higher the star formation rate enhancement, or in this case, closer you are to actually merging, the higher your star formation rate. So for the first time, we can do this with time estimates for pre-mergers and post-mergers. And I think I'm running out of time, so I should probably summarize. There are different ways to find galaxy mergers. Machine learning is great, but not always necessary. Simulations give us an idea of what the truth is. But whatever you use, fine structures are what neural networks typically look for, although simple profiles do contain information. And now, for the first time, we can get merger times within about 300 megayears, and we get the first observed trace star formation rate with merger time. And I will leave it there. Thank you for your attention.
Thank you very much, Will. Do you have any questions or comments? Okay.
So when you consider the galaxy mergers, the galaxies usually contain black holes in the centers. Can you get an estimate of the galaxy merger rate density, so the number of mergers per volume per time? And can you get anything about the cumulative gravitational wave background and the variable frequency from there? And you know, how does this rate compare to simulations?
So this is not something that I looked into. I don't really work with gravitational waves, so
the measure intensity, that's the
yeah. I'm more interested in what galaxy mergers do rather than their density. So I've not looked into this precisely, so I can't really give you a good answer, unfortunately. So something interesting to look into at some point.
I was wondering if you do any work with much closer objects, like, okay, here many people are working on LMC, SMC, and there are some like some results showing that LMC is a merger actually with some other galaxies. Is that anyhow of your interest?
So I normally go from a statistical perspective. So I like big numbers, and the very, very local universe, we don't have number statistics. So, I mean, with respect to the LMC, SMC, they are probably some distinction in the process of merging. Not an expert in this kind of close galaxies, but I think, if I remember correctly, they're close enough to be merging with our galaxy. So I don't know specifically about if they have previously merged with some small galaxies. In this case, the SMC LMC with the Milky Way would be what we would call a minor merger. So the mass ratio is somewhere in the order of 1 to 10. But it's entirely possible that LMC, SMC have merged with similar sized galaxies to themselves. So they've undergone, they're small dwarf galaxies, but undergone major mergers. I know people do work on this kind of thing. I don't personally, but I know there's literature that discusses this kind of thing.
Right, so if you show this to a biologist, he would say this is cell division, not merging. Okay? I believe in gravity, we have simulations, of course, but the question is from the observational point of view, do we like, after we find all those merging galaxies, do we like really learn about what's going on? Is there any perspective of locating the post-merger galaxies?
So locating post-mergers, yes. The difficulty is in a post-merger galaxy, when it's just finished coalescence, the galaxy is very disturbed. And then it kind of relaxes over time. And you have a relatively speaking, short period of time to find them when they're very disturbed. There is work by another group that has done something similar to this, where they get the merger time for post-mergers, and for pre-mergers they use galaxy separation. So you can find post-merger galaxies, but only within relatively short amount of time from when they've done. So like half a gigayear to a gigayear, roughly. So 500 megayears to 1,000 megayears is roughly the range that we can find them. Then after that, certainly in the larger surveys, we don't get the depth to be able to see the faint structures that probably still exist around them. So I was at a seminar earlier today, was discussing low surface brightness. So you might be able to find them if you're very careful, more than 1,000 megayears after the event. But typically speaking, we can find them, just not that long after.
Have any questions online?
We don't have.
Okay, I don't see any hands up, so thank you very much. Next week we have Andrei Sharman about radio pulsars, like, right? Oh, thanks. Thanks. Hello, thank you very much. And actually, it brought me to another invitation for you, because we have something that is called statistical